Watch until the end if you want to learn how to make something that looks like this in Godot 4.1. Start by creating a new project. Make sure to choose forward plus rendering if you want the optimal HD-2D effects. HD-2D does work with mobile renderer, but requires some tweaking in parameters. Take note, HD-2D won't work in compatibility renderer. If you are planning to make a web game in HD-2D style, it might be time to look elsewhere. Here's a quick comparison of the same scene in different renderers. Next, set up the input mapping. I'm using these action names for the player controls. To add a new input, just type in the action name and select the corresponding keys. Each action can have multiple input keys. I'm making a HD-2D games inspired by Octopath Traveler. Hence, it makes sense for us to try to identify key elements for this style. Here's a screenshot from Octopath Traveler. What do you think are the key elements? The most obvious one is that character are 2D pixel art. Also, the environment is made of 3D models. We have depth of field, which creates the blurred background. We have light rays, which adds to the ambiance. We have lighting and shadows, which makes the world look realistic. We have bloom, which adds pop to bright areas. Lastly, we have vignette, which darkens the corners to help the player focus on the center. Let me know what other elements you think are important for this style in the comments. Having identified the main elements for HD-2D games, we can go ahead and create a scene for each of these main components. Start by creating a root node in a new scene using 3D character body. Add a 3D collision shape node so the player won't fall through the floors or pass through walls. For collision to work properly, you will need to define the shape. For now, let's stick to the traditional capsule shape. Add a 3D sprite node to represent the character. Add your sprite sheet to the texture. I'm using a 5x5 sprite sheet, so I will set horizontal and vertical frames to 5. My sprite sheet only have animation for front, back, and left facing. To change the left facing to right facing, simply set horizontal flip to true. The frames property is used to set the current frame. As you increment it, you can see the flipbook animation kicking in. Next, add an animation player to update the frames. Create a new animation and name it walk. Add the frame property to the animation. I've experimented with the timing and found 0.15 seconds per frame optimal. We can update the snap to make it easier to align each frame. Tip: you can scroll while holding Control to expand or contract the timeline. Since my sprite sheet has 7 frames per direction, I'll add 7 keyframes to the animation timeline and set the animation cycle duration to 1.5 seconds. Once we have our frames created, we need to update the frame values. Make sure to enable loop to keep the animation playing. This is just a demonstration of the principles behind animation. It's going to be tedious to keep doing this step for different walking direction, so let me show you another way to do this. Start by adding a script to the root node. Create an export variable, which makes it accessible in the editor. Add a new track based on this variable. Replicate the same setup as earlier. Next, let's create a function to handle our animation. In the default state, direction will be a 0 vector. In this scenario, we want the animation to stop playing and set the frame to 0, which is the resting position in our sprite sheet. When the player press either of the directional buttons, the direction vector will no longer be 0. We can use this condition to start our animation. Next, we want to add the logic that determines the first frame of our animation. From our sprite sheet, the first 7 frames are walking towards the screen. The next 7 frames are walking away from the screen, and the last 7 frames are walking towards left. Based on these information, we can update the facing and the horizontal flip according to movement direction. Finally, we will update the frame value by passing in the animation frame property, multiplied by the facing and the number of frames our sprite sheet have. With the animation and movement code ready, let's set up the scene for camera movement. Add a 3D spring arm node and create a 3D camera node as a child to the spring arm. Create a script and attach it to the spring arm. Let's start by triggering rotation with the player input. We can just update the Y rotation, but this sudden change in camera rotation makes for bad player experience. Instead, let's use tween to create smooth transitions. For setup, we need instantiate a new tween. Set the transition and ease type. We use the tween by passing the target object, property, final value, and duration. To tween the camera rotation left and right, we simply set the trigger action and the final value in radians. I've also added a reset rotation for good measure, which is triggered by pressing both left and right rotation. To handle zooming, we want to update the spring arm length in increments of 1. To prevent unlimited zoom, I'll set the trigger boundaries to a length of 1 to 4. When the spring arm length is 0, the camera is in first-person perspective, so let's add some height to improve the game feel. Finally, since our camera now have different rotations, we need to update our character movement code to also consider the camera orientation. If your sprite sheet looks blurry and the color seems off, you would need to re-import your image. Set the compress mode to lossless. Disable detect 3D compression, and it should look way better, and save it as the default settings. To get the sharp and crisp pixel edges, go to Project Settings and set the default render filters to nearest neighbor. To recap, after having the character ready, the next thing we need is to build a 3D world. One of the easiest way to build a level is through grid maps. Setting up a grid map would make your level design as fun as Minecraft Creative Mood. Instead of mining for blocks, you have to create them. Out of all the basic building blocks, a simple cube and triangle can get you very far. We start by creating a base scene for our cube. Create a 3D mesh instance and set it as a cube. Add a static collision node and a 3D collision shape. Set the collision shape as a cube. Create a material. Set the material as your tile. You can use any of your pixel art tiles as the material. If you notice any weird patterns, set the UV coordinates to 3, 2, 1. In case you haven't set the default filtering to nearest neighbor, you can set it directly on the material. Save a copy of this material. Duplicate it when you need a new tile. That way, you don't need to configure the settings over and over again. Once you have all the materials, start creating inherited scenes from the base block. In Material Override, simply drag and drop the different materials, and it would apply to the new block. Name your block and save it. Repeat until you have all your blocks ready. For the slope block, we can use a prism for the mesh and set left to right as 1. Since there is no prism collision shape, we need to automatically generate a tri-mesh static body for it. Similarly, create as many inherited scenes as you need. Once you have all the building blocks, create a new scene and drag all the blocks into it. Create a mesh library from this scene and the preparations are ready. Next, create a 3D scene for your level. Add a grid map and choose your mesh library as the source. Some useful shortcuts for designing your level. While holding Shift, you can click and drag to select areas. While the area is selected, use Ctrl+F to fill the selected areas with your active tile. When tiling asymmetric blocks like the stairs, you can rotate it along the Y-axis to get the desired orientation. While holding right-click, you can use WASD to fly around the map. Hold Shift to speed up the flying. If you see some gaps in your grid map, you can resolve this by setting the grid size to match your block size. You would also need to make sure your blocks have the same size, which is why we created inherited scenes for all the base blocks. Not only would that keep properties consistent, it also allows changes on the base scene to be applied to all inherited scenes. To add props to the level, we start by creating a base scene using a 3D sprite. Some of the key properties would be setting Y billboard, turning on shaded flag, setting alpha cut to opaque prepass so that it will cast a shadow and texture filter to nearest neighbor for the crisp pixel art look. You can add collision to it if needed. You can also import 3D models directly from Blender files. To do that, go to Project Settings, scroll down to File System, and enable Blender. Once that is done, you can open blend files directly from the Godot file system and save the mesh as a scene. To add collision to these meshes, simply create a tri-mesh static body in the same way as the prism stairs. And this is pretty much all the basics you need to get productive with 3D level design. If you followed the tutorial up until now, this should be what you have. A pixel art player that can move around in a 3D world, but it is still nothing compared to the Octopath style. To bring it one step closer to the Octopath style, add a directional light. Turn on the shadow and adjust the angle of the light to our liking. If you want a softer shadow, reduce the shadow opacity and increase the blur. If you want to make your pixel art shadow blocky, set split 1 to 0. If you notice your shadow having splits, turn on blend splits. Next, add the most important component for any 3D games, world environment. I've experimented with a few different sky settings, and I found that panorama sky are the best for the Octopath style, especially one that is painted stylistically. To set up your own skybox, add a world environment, set background mode to sky, set sky material to panorama, and add your skybox as source. Next, go into tone map and choose a rendering mode that fits your skybox. For my game, I prefer the softer diffused look that Filmic renderer create than the strong, high contrast look of Aces. Enable screen space ambient occlusion to increase the shadings along corners and edges. Enable screen space indirect lighting to enhance the realism by simulating indirect bounce of light. Next, enable glow for the bloom that is a highlight in the Octopath style. Just be careful not to go too far with it. Personally, I like to keep the bloom small to make it subtle, something around 0.03 to 0.06. Finally, for the blurred background effect, add a practical camera and enable depth of field. Set the blur amount to something that you like. As always, I prefer a subtle blur, so something around 0.05 to 0.1 is what I usually go with. Having the depth of field on in the level editor is a pain to work with, so once I've gotten the blur that I want, I'll save the camera attributes and set it on the player. That way, the depth of field will only take effect on runtime on the player's camera. Next comes the vignette. There's so many different vignette implementations that there's not much point in reinventing the wheel. I went to Godot shaders and tried out a few vignette. Some of the shaders are outdated, so you might need to make some tweaks for Godot 4. I went with this vignette by Random Dam. To make it work in Godot 4, we just need to change hint color to source color and add a 2D sampler. Finally, we have the God Ray implementations for the extra oomph. I'm using one of the simplest way to achieve this effect, using particles. Start by creating a GPU particle node. Add a draw pass which contains your texture. Choose a quad mesh and add a standard material. Set your particle texture in albedo. Set your vertex color to use albedo. If you are using a black background and white subject texture like me, you would need to set transparency to alpha and blend mode to add. Turn on local coordinates in drawing so we can rotate the particle node to emulate different light angles. Go to time and increase lifetime value for more persistent rays. Add some randomness to make the rays look more natural. Finally, increase the draw pass length to create the illusion of a light ray. After setting up the draw pass, go into Particle Processor and set the emission shape to a box. This allows the particle to spawn within a bigger area. To make the particles easier to work with, set gravity to 0 and add movement through linear and radial acceleration. Just play around with the numbers until you find something good. For more natural light rays, we can increase the maximum scale for more variation and add turbulence for more randomness. Finally, set the color of your light rays here. By the way, the source code including the assets are available for my Coffee monthly supporters under the Serious Game Dev tier. For this specific tutorial, supporters had access to source code since 3 months ago. They also get access to my drafts, such as this whiteboard.